Generative models are measured on mode coverage and fidelity. Generative adversarial networks land in the high-fidelity, low-coverage quadrant, suffering from mode collapse. Variational autoencoders occupy the high-coverage, low-fidelity corner, generating blurry samples. Diffusion models resolve this, achieving GAN realism with VAE coverage. This performance is the result of systematic assembly. Diffusion pulls specific tools from the architectures that came before it, taking the stability of the VAE family and the sharp goals of high-fidelity models, and integrates them into one cohesive system. The foundation of this architecture rests on a specific premise. The most reliable way to generate complex structure is to first learn how to systematically destroy it. This is the forward process. Over a fixed schedule of hundreds of individual steps, the model takes a structured data point and incrementally injects a calculated amount of Gaussian noise. It repeats this until the original structure completely dissolves into pure static. The reverse process is where the neural network actually learns. Starting with that pure static, the network removes a fraction of the noise step by step, gradually pulling the original structure back out of the chaos. By dividing generation into hundreds of tiny denoising steps, the network bypasses adversarial training entirely. It solves a long sequence of well-posed, stable regression problems. To train this network efficiently, the system needs to calculate the exact state of a corrupted image at any given point in that destruction process. This precise addition of noise is governed by equation 7.1. This visualization of equation 7.1 shows how Gaussian arithmetic streamlines the process. Because a sum of Gaussians remains a Gaussian, the math allows us to bypass sequential iteration. We can take a clean data point and execute a direct mathematical jump to a highly noisified state at any random time step. This closed-form property means the training loop can pull a clean image, pick a random time step, and instantly calculate the precise noise needed. A single batch trains the network randomly across all possible noise levels simultaneously. Without this property, a model would have to manually calculate hundreds of preceding steps just to simulate a single noisy state, making training computationally paralyzing. For the reverse process, the system relies on a deep neural network, typically a convolutional unit, to perform the actual denoising at every step. But the unit does not attempt to predict the clean image. In the denoising diffusion probabilistic model, the network is trained strictly to predict the exact matrix of noise that was added to the data. We can see this mechanic in equation 7.2. The objective isolates the difference between the true added noise and the network's predicted noise. The model minimizes that gap using a plain, stable squared error regression. Mathematically, predicting that noise is identical to estimating what statisticians call the score, the gradient of the log density of the data distribution. In this score-based view, generation becomes a process of navigating a vector field. Points of pure static follow the gradients, moving from empty regions toward high-density clusters to form organized shapes, a process known as Langevin dynamics. While they use different vocabularies, DDPM noise prediction and score-based navigation describe the same underlying algorithm. Whether the model is predicting a noise matrix or following a vector field, the actual computation remains identical. While the mathematics are elegant, running hundreds of forward and reverse steps on a high-resolution pixel array requires millions of calculations at every single step. The engineering breakthrough that solved this bottleneck is called Latent Diffusion. A variational autoencoder compresses a large 512 by 512 pixel grid into a dense 64 by 64 representation. The computationally heavy forward and reverse diffusion processes run exclusively inside this smaller space, before the VAE decoder expands it into a full-resolution image. By marrying diffusion's mathematical stability with VAE compression efficiency, the industry unlocked the ability to run state-of-the-art generation on standard consumer hardware. Left alone, an unconditioned diffusion model generates plausible but random structures. To steer the output, cross-attention mechanisms inject encoded text embeddings directly into the unit layers. But standard conditioning has an inherent flaw. The resulting generations often followed the injected prompt text loosely, drifting away from the specific description. To force strict adherence to the prompt, the industry relies on an applied mathematical fix called classifier-free guidance. During generation, the U-Net computes two parallel outputs simultaneously, one prediction utilizing the text prompt and one completely unconditioned prediction based on the noise alone. Equation 7.3 maps the relationship between these two outputs. The model calculates the difference between the unconditioned state and the text conditioned state and extrapolates away from the unconditioned point to reach a final, much further target destination. The guidance scalar determining the length of that extrapolation serves as the central fidelity versus diversity dial, allowing engineers to trade generative variety for precise textual accuracy. Diffusion is not strictly an image generation technique. It is a general statistical recipe for sampling from any highly complex, intractable distribution. Applied to audio generation, the exact same mathematical framework operates on two-dimensional time-frequency spectrograms rather than pixel grids, producing high-fidelity speech and music. In video generation, the framework requires 3D or factorized space-time attention. As seen in this tracking sequence, the model denoises an entire clip jointly. This ensures temporal coherence, maintaining physical geometry across hundreds of sequential frames. The framework also scales to the hard sciences. Researchers use diffusion to generate novel 3D atomic coordinates, designing completely new protein structures from scratch. Because the core mechanism operates on abstract latent data rather than specific sensory inputs, diffusion functions as a universal modeling engine across domains. The architecture has one remaining disadvantage when compared to legacy GANs: the inherent slowness of sequential multi-step sampling. To circumvent this bottleneck, the field has developed flow matching and consistency models. This chart compares the sampling paths. Instead of mapping a stochastic multi-step trajectory, these modern techniques map continuous time trajectories. They train the network to jump from noise to the final data point in just one or two deterministic steps. As these single-step techniques mature, diffusion will absorb the final advantage of adversarial networks. It stands as a synthesis of decades of research, combining the stability of its predecessors with the speed required for real-time use.